Have you ever stopped to think what's really going on when you send Bitcoin? Well, today, we're going to peel back the layers of a simple transaction, and what we're going to find is a powerful secret hidden deep inside. It's a simple programming language that literally defines the rules of money.
So let me ask you this. When you send some Bitcoin, are you just handing someone a digital dollar bill, or is there something way more sophisticated happening just under the surface? The answer, you'll see, lies in what you are actually creating.
You see, at its very core, every single transaction on the entire Bitcoin network has to answer two really basic security questions. First up is authorization. Who is even allowed to spend this money? And second, authentication. How do they prove they're the right person? Now this is where the genius of Bitcoin comes in. It doesn't just answer these questions with a simple signature. No, it uses a hidden programming language. A language that actually sets the rules for exactly how that money can be spent. This language is called, simply enough, script. And it's not like Python or JavaScript, nothing you'd build a website with. This is a very, very specific tool, and it's designed for one purpose and one purpose only, to create an instruction manual, a kind of puzzle that someone has to solve to spend the Bitcoins that are locked up in a transaction.
And here's the thing about script. It's intentionally limited, and that's actually its greatest strength. It's super simple, so every single computer on the network can process it without breaking a sweat. It doesn't have any loops, which is a huge security feature. It prevents bad actors from freezing the network with some kind of infinite task. And it's what we call stateless, which just means the outcome is always predictable. Every node gets the same answer every single time. No ambiguity.
So, okay, how does the network actually run through these instructions? Well, it uses a beautifully simple data structure. It's called a stack. The best way to think about a stack is to picture a stack of plates. You can only do two things: add a new plate to the top or take the top plate off. That's it. So Bitcoin just processes a script from left to right, placing data onto the stack and then using special commands, we call them operators, to work with that data. Let's walk through a super simple math puzzle to see this in action, okay? Here's our script. 2, 3 API add, 5 API equal. First, the network reads the number 2, and bam, it pushes it onto our empty stack. Next up, it reads the number 3 and pushes that right on top of the 2. So now our stack has 2 items on it. Easy enough. But now we hit our first command, our first operator, op add. What it does is it pops the top 2 items off the stack, that's the 3 and the 2. It adds them together to get 5, and then it pushes that single result, 5, back onto the stack. All right, moving right along to the next item in our script, the number 5. The network just pushes this onto the stack, right on top of that other 5 we just calculated.
And now, for the grand finale, the op_equal operator. It pops the top 2 items, it compares them, and since they're both 5, it pushes the value true onto the stack. A final result of true means, hey, puzzle solved, the transaction is valid.
Okay, that was a pretty simple math puzzle, I get it. But what's so incredible is that this exact same logic is what powers almost every standard Bitcoin transaction you have ever made.
You see, a standard Bitcoin address, it's actually a puzzle in disguise. It's called pay to public key hash. And when you send Bitcoin to that address, what you're really doing is creating a digital lock. This lock is tied to something called a public key. You can think of that like a mail slot on your front door that anyone can drop mail into. The script for that lock basically says only the person who has the matching secret private key, the only key that can open that mailbox, is allowed to spend this money.
So, how do you solve this puzzle? Well, the spender has to provide 2 crucial pieces of evidence: their public key, that's the public mail slot, and a digital signature, which is like a unique, unforgeable seal created with their secret private key. The script then runs a 2-part check. First, it creates a unique digital fingerprint, called a hash, of the public key to make sure it matches the address on the lock. If that checks out, it moves to part 2. It verifies the digital signature to confirm that the real owner, and only the real owner, approved this exact transaction. If both checks pass, the puzzle's solved.
Now, P2PKH is great for you and me, but what about more complex situations? What if a big company needs, say, 2 out of its 5 partners to sign off before any money gets spent? You can actually do that with something called a multi-signature or multi-sig script. It's an incredibly powerful feature for things like corporate security. But there's a catch. The script itself, listing all 5 of those public keys, is really long and clunky,
And that creates a huge headache for the customer who has to pay them, because it makes the transaction big and much more expensive. So this very practical problem, it demanded a much more elegant solution. How could Bitcoin support these amazing complex rules without dumping all the cost and complexity onto the person who's just trying to send the money? The answer was a truly brilliant innovation called Pay-to-Script Hash, or P2SH. The idea is just beautiful in its simplicity. Instead of putting that entire, long, clunky multi-sig script in the transaction, you just put a tiny 20-byte hash of it instead. And this table just illustrates this shift perfectly. Just look at the sender's script on the right. With P2SH, it becomes tiny and totally standard. And it doesn't matter how complex the rules are underneath. All that complexity, the long list of keys and signatures, gets shifted to the person who's spending the funds. They only have to reveal it when they're actually ready to unlock the money. That full, complex script, that's called the redeem script, and it's kept totally hidden until the moment of truth, the moment of spending. The network then just has to do two simple things. First, it hashes the redeem script that was just provided to make sure it matches the hash from the original transaction, and second, it runs that redeem script to make sure all the signatures are valid. Simple as that. Okay, let's pull back for a second and look at the bigger picture here. Why does any of this hidden language stuff really matter? Well, because if stripped, Bitcoin isn't just digital cash, it's programmable money. Every transaction is a tiny, secure computer program. It's a puzzle box, locked with rules. The stack is that simple, predictable engine that solves all these puzzles. And innovations like P2SS show us how this amazing system can evolve to make even the most complex rules practical and efficient for everybody. This flexibility, right at the foundation of Bitcoin, is what makes everything possible, from simple payments to complex smart contracts, and it leaves us with one final, pretty mind-bending question. If money itself can be programmed with its own set of unchangeable rules, what does that change about how we trust, how we transact, and how we build our entire financial world?